All right. Hey, everybody. Welcome back. Um, Today we're going over section 1.4 in Vakil, which is on adjoints. And so I'm hoping that we can maybe start Abelian categories tonight because this is a pretty short section. Um, and so Abelian categories are really what set up really the notion of like sheaves of varieties are going to be like what we care about with abelian categories. They also this is what we're going to initially define homology and cohomology on, which are going to be very important tools later. So all in all, this should be fun. I'm also just kind of for you too, but anybody in the YouTube comments section who decides to watch through all these, if I run like another kind of like ancillary seminar that's like a remedial seminar on category theory, and it's going through, there's this book I've been looking at called it's something like Derived Methods in Categorical Commutative Algebra, I think is the name of the book. But it's like a 2,000 page tome that I asked for Christmas so that I could get more into like derived category theory, which is pretty important for homological algebra. I think it'd be kind of cool to do that. And then also I've been reading through this book on Galois cohomology and class field theory, and it's been really interesting so far. Um, and I haven't like been doing homework or anything in it, so I'm not ready to like teach a seminar on it, but maybe just as like a hey optional thing if you're interested in cohomology. So anyway, offering that up now over winter break. So just kind of going through last time, remembering some stuff. So we talked a while ago now about fibered products. We said that fibered products are really the thing in this diagram, and there's two things. So the definition of a fibered product is it's all of the stuff in the pre-image of alpha and beta through Z that agree in Z, and it's in the product space. And so it's like pairings of things that agree through alpha and beta. And then the universal property of fibered products is that any category W that maps into X and Y has to factor uniquely through the fibered product. And so we did a bunch of stuff for this. Um, that goes here. We did the base change diagram of pain and suffering. um, Fond memories, I'm sure. Yeah, that's horrible. Um, we talked about fibered co-products being just kind of the dual like arrow reversing thing going on here. So co-products are like the arrow reversing thing going from X and Y factoring through the product into W. And then fibered co-products kind of work the same way. So that's kind of intuitive. And then fibered tensor products of A modules have ring structure. That was kind of like something we didn't prove, but that we said, okay, this kind of makes sense from how we've thought about fibered products so far. Then we talked about monomorphisms. So a monomorphism is this thing from x to y pi, such that basically if you have two compositions of morphisms from z to x and x to y, that it really means that they're the same morphism. And then epimorphism is kind of the dual of this, where we reverse all the arrows. And this is kind of our notion of injectivity and surjectivity, respectively. So monomorphism is injective, mono kind of tying to one. That's how I remember that. And then epimorphism is surjective. Um, Now, notably, injectivity and surjectivity imply things about the object that the arrows are going into that maybe the actual morphism itself doesn't imply. So we don't, this is kind of why we separate out injectivity, surjectivity. Um, but yeah, um, essentially you can think of them unless we need, that slight difference, as like injective and surjective morphisms. And then Yoneda's lemma was that you can recover objects in a category by knowing the maps into them. And we expanded on this in the next lecture, where we went through the formal thing on Yoneda's lemma. And then we said, okay, now we can produce like a functor category, where the objects are contravariant functors. I think I meant to write covariant functors. Um, and then the morphisms are natural transformations of the functor objects. And then the Yoneda embedding is like a fully faithful functor um, from a category to its functor category. And then we said that the Yoneda embedding was contravariant. Limits and co-limits were like the next thing that we talked about. And so we defined a small category as like this thing where the objects and morphisms form a set, and then like everything we've kind of thought about as an example of a category has been a small category. And then we said, okay, well, universal products, like universal diagrams are kind of nice, and like universal properties of diagrams are nice because if we have a category that looks like this, then we can define the limit like in certain ways. And so really the thing that like inspired the idea of a limit is it's a way of collecting all of the things that agree in a diagram, right? So like excluding all of the notation, it's very important. The intuition behind the limit of a category is it's a way of bundling all of the objects and morphisms in a category that agree. Um, and so like universally, the limit of a diagram that looks like this is the fibered product. The limit of any collection of disconnected nodes is the product. So we've been thinking about limits of categories this whole time. So the same way that fibered products collect all the things which agree in like the end of the thing, or like the product collects all the things that agree just in terms of pairings of things, like the limit of a category is very intuitive. The co-limit is a little less intuitive. So the co-limit is the arrow reversing of the limit. Oh, yeah, and then we used the property of limits to prove the base change diagram of pain and suffering much more easily. It's still the base change diagram of pain and suffering, but a little bit less. Um, and so yeah, the limit of a diagram is like the limit of the subdiagrams. We talked about formal power series. So a formal power series is the collection of infinite sums with coefficients in the module over a variable x or like xy. And so it looks like this, where like it is an initial object in its category of like A modules. Um, and so this is kind of like saying, oh, this is an example of a limit of a category. And then actually we call it the completion. So for people with real analysis background, when we talk about Cauchy complete spaces, we say, okay, well, a space is complete if all of its Cauchy sequences converge. Well, a space is also complete if all of its formal power series converge. And that is actually exactly kind of what this is as an equivalent definition. So when we talk about like K being an algebraic closure that we work out of for affine n space, what we really mean is that K is a space in which all formal power series and the variables that we choose converge. And so, yeah, that just kind of works like this. Talked about the p-adic integers. These will come up later, so maybe we'll just come back and reference them. But they're the limit in the category of rings of like of finite fields of order p to the n. And this shows up in cryptography. So limits don't always exist. Easy to check if they do. Usually they show themselves kind of as like fibered products. That's the more common way of thinking about them. Or like fibered products of fibered products, which is a weird way to think about it. But we showed that towers of Cartesian diagrams or pullback diagrams were pullback diagrams. So you can think of it as like if you have a big tower of Cartesian like diagrams, it just stacks up eventually. And eventually the thing that is like the furthest back is the inverse limit. So hopefully that's clear. Yeah. It's also like in the category of sets, it's the thing that contains solution sets to morphisms. And then holds for modules and rings. The co-limit is the going forward. And there was a really great thing at the end of this. Kind of like the intuitive way to think about co-limits is that like localization is a co-limit. It's like it pushes down. So like the limit was the thing at the top left of the diagram that like had all the things that agree. The co-limit is like the localization by all of the things that don't agree. Um, and so in abelian groups, like 5 to the minus infinity is the co-limit of all of the chains of like z and 1 over 5z and 1 over 25z and so on. We talked about filtered sets. Um, yeah, okay. Yeah. So here's the thing that Vakil says about colimit. So colimit, an element of a colimit can be thought of as an element of a single object in the diagram. Um, and so an element of a limit can be thought of as a family of elements of each object in the diagram which are compatible. An element of a colimit can be thought of um, or has a representative that is an element of a single object in the diagram. Um, so yeah. Okay. Now we're ready to go back into adjoints. Any questions on all of that that can be answered briefly? Okay.
None on
Oh,
my end.
okay. So, adjoints. We next come to a very useful notion closely related to universal properties. Just as the universal property essentially up to a unique isomorphism determines an object in a category, assuming such an object exists, adjoints essentially determine a functor if it exists. Um, so as an initial definition, let me do this in yellow. Um, so two covariant functors f from script A to script B. I'm trying to make this as scripty as possible. Um, and then a second covariant functor from script B to script A um, are an adjoint pair or are just adjoint. Um, if there exists a natural bijection, for all A in script A um, and B in script B. And this bijection is tau AB, I think that's little a and little b. From the morphisms of script B with some functor of little a to b into the morphisms of, and I need to make this more scripty, script A from A to G of B. Where F is the left adjoint and G is the right adjoint. So this is the left adjoint. G is the right adjoint. And so when we say natural, of course, it's category theory. Natural does not mean natural, but we're going to show that it makes sense. Um, so, um, what what does natural mean? Normally, when we mean natural, we mean that like we have a domain that naturally partitions itself And so like the quotient topology from some topology is like a natural bijection that's just or a natural injection that's no a natural surjection that's assigned by like where in the partition you land, right? But like okay, um I introduce the natural bijection of pain and suffering. Um for all f um from A to A prime in script A, we require the following diagram to commute, and that's actually not the entire thing. So the morphisms of script B um, with our left adjoint of A prime to B and B has a morphism, and we're going to explain what the notation is here, but I'm just going to draw it first. Um, F composed with this F star thing to the morphisms of script B to F of A, comma B to the morphisms of script A, comma, the right adjoint, and this is by tau AB, and then the morphisms script A prime with the right adjoint, and then this goes by just regular F star. This goes tau A prime B. Where, well, I guess, so this commutes, and then defining our morphisms here, and for all little g from B to B prime in script B, a similar diagram commutes, and then clarifying the notation, F star is the map induced by F from A to A prime, and the functor composed with F star is the map induced by the functor composed with F from F of A to F of A prime. And then naturally the same thing carries over for G. So, okay, what are we saying here, like with the F star thing? Okay, well, this is saying the functor carries over information about the object and the morphisms in this first category, script A. So we're carrying over this to be like whatever the image of the functor is in script B. And then that should be between the functor of A and the functor of A prime. Right. So this is kind of like our notion of, all right, this thing is going to carry the information over for us. Now, determining what this other thing for B and B prime looks like, right? Well, I'm just going to do this in orange. This would be F of B prime, comma A. F star can stay the same. Instead of this, it's going to be G, maybe G star. And then it's going to be, right, it's not going to be this. It's going to be G. G of B, G B comma A. This is going to be script A here. This is going to be script A here. This is going to be... No, that's not script A. No, that is script A. That's script B. That's script B. This should be B prime. This should be F of A. This should be G star. The taus, I think, can stay similar. This should be tau A B prime. Tau A B can stay okay. And then here, this is as follows. And then, so the orange is the one diagram. Yeah. So does this make sense to everybody about like where this comes from, how it works, how it makes sense?
Yes, it does.
Okay. And does the notion of like adjoint pairs make sense?
It really does compared to everything else.
Okay. I won't argue with that. um yeah. Oh, I don't want to do that. Ugh. Okay, let me see. I'm looking at this next exercise, trying to decide if it's particularly important. For each A, there's a map eta of n A into the composition so that any G corresponding tau of G is given by the composite. Okay, I'm just going to state this as a theorem. I don't think we need to prove it. Unless it doesn't make sense. So tau AB as initially constructed in blue has the following properties. So for every, I think regular A, yeah, for every A in script A, there exists a map, and I suck at drawing etas. So that's an eta. Sub A from A to the composition of G and F of A such that for every G from FA to B, the corresponding tau AB of G from A to G of B is given by the composition A by eta sub A, G composed with F of A, because remember F of A lives in B. By capital G composed with little g in to G of B, recalling that G goes back into A. Um, um, and then similarly, there exists a map epsilon of B from F G of B into B for every B in script B, such that for any F from A into G of B, tau AB inverse of script F from F of A into B is given by the composition F of A by F composed with F, F, G of B, epsilon B back into B. Okay. What is this ultimately doing? Well, we're sending stuff kind of as a natural isomorphism from things in this script A category um, through a functor from A to B. Within the category B, we're taking the image of this object, morphisms between the two, taking it back through to the morphisms of A, through the image of like the original A, and then G of B. And so we kind of have like a way of relating the morphisms of these two objects. And I just realized this is actually very pertinent to something I'm doing. Oh, that, damn. Okay. Sorry, I had something click for some research I'm doing. Um, anyways, then in terms of this theorem, um, the natural bijection has the property that we can build it out of compositions of things, and that just is kind of by construction. Um, okay, so as an exercise, suppose M, N, and P are A modules, where A is a ring. Describe a bijection under the morphisms from M tensor product through A of N to P, and then morphisms between M. Oh, that's terrible. So what we want to do is we want to put something like let phi be in this And then we're going to want to describe an adjoint pair. Um, let F from A to this other thing. And we'll want to describe this in a way um, that it's not problematic. So I'm going to flip back to the section on tensor products, which is actually quite a while back. Um, so really this is like we want to say that want to show that's weird. It's not updating my Teams broadcast anymore. Hmm. Oh, Notability just decided to update in the middle of this. So whenever it decides it's done. Why is it saying I can't record? Hold on. That's so weird. This is really weird. Teams is being updated. Okay. You guys have been able to see this whole time, right?
I have.
Okay.
Me too.
Well, suddenly it doesn't like that. The hell? I'm gonna stop recording. But that. What? Okay. You guys can see it now, yeah?
I can.
Okay. Alright. Sure. Okay. Cool. Well, we want to show that f of phi is well, we want to define f of phi actually. Before we say we want to show anything, we want to say, okay, let's find a map. So f is this. or phi is this thing where phi of this product of A modules into an A module, and I'll just say is maybe equal to or I guess is maybe equal to psi. From M to a set of morphisms of NP. Does anybody know or have an idea of what I should fill in here?
I don't.
Sorry, nor do I.
Hmm. Well, it has to go from M to something in like HOM NP, that's just weird. And in terms of a bijection, we need something that is surjective, so every such map gets hit. We need something injective so that any two maps that are the same over here are the same over here. If we're thinking about morphisms between N and P, we want to use the universal property of tensors is the hint. Where is the unique property of tensors? Or universal property of tensors? Hold on. If M is an A module, A to B is a morphism of rings. That's no, that's universal property of tensor. Given M cross N, there is an A bilinear map from the product to the tensor product, unique up to unique isomorphism for any A bilinear map from the product to T prime, factors uniquely through T. Okay, so I'm going to put this all out. So recall universal property of tensors. Basically, M product N T to the tensor product through A going down to T prime. This is T prime, this is T. Nope, that's not T. This is our unique factorization F. And then the universal property is that the tensor product and the map into it from the product is unique up to unique isomorphism, meaning that any map T prime going down into this other T prime. Oh, so, okay, I get it now. I understand how we use this. Is it clear to you guys where this comes in?
Not exactly.
Okay. What we're going to use is that essentially, um, we're taking like f of phi. This is getting sent to, well, to f of phi, right? Um, but this lives inside of, well, okay, hold on. It's going to be easier if we do this with the entire thing and then build a specific example out. So this thing has oh wait, nope. There we go. M product N P, right? And so this is T. Well then this is little t. This is T prime. And then big T prime is hom A. This thing. And then by universal property, then we can just find anything in here, and it's going to factor through T and F, where F is the functor that's our bijection.
Okay, that makes a lot of sense now.
So now it says actually find one. I'm just going to say we move this thing around, right? And say, okay, well, phi of, or I guess rather, sorry, hold up. Phi from M cross N to P gives T prime going, or T prime of phi is equal to psi, which goes from M to the A hom of N and P, where phi of like M naught, comma, N naught is equal to P naught, gets sent down to phi of M naught is equal to G, no, sorry, this gets sent down to psi. There we go. Psi goes from G of N naught the image of G should be the n naught of P. N to P by G n naught is equal to P naught. And then that gives us a bijection. And is that clear how that ends up being a bijection by construction?
Yeah.
I mean, it's a headache. Don't get me wrong. Like functor categories suck, but they're very useful. But they suck to work with sometimes. Um, yeah. And so basically, we're given that this will factor by universal property of tensors through this thing. And I'm pretty sure that that is the answer that they're looking for. Does that make sense?
Yeah, it does.
Any logical holes that anybody is seeing that I might not be?
Not that I know.
Okay. Um. So theorem. Um. Any any tensor product with n and then the amorphisms of n with the thing are an adjoint pair. And this is pretty much like saying the thing above here. Um, so I mean this is just kind of a restatement. But this is called tensor Hom adjunction. Actually, I think this is a little more general. Tensor Hom adjunction. Okay. So, hmm. Okay. Another example of adjoint pairs. You can create a B module. So if B to A is given by some ring morphism, and if M is an A module, then we can create a B module B, or MB. B module MB. Um, and this yields a functor dot B from A modules to B modules, which is right adjoint is a right adjoint to the B tensor product of A as a functor. And then the easier way to characterize this in other words, there exists a bijection from the B tensor product of n with A to M, which is isomorphic to the B Hom from N to MB. So the thing that kind of moves around here, we have our A. This is a B tensor product, and then B modules and B morphisms. And this is kind of an adjoint pair. So just as a remark, left adjoints determine right adjoints up to natural isomorphism. And then eta and epsilon here. Eta is called the unit, and epsilon is called the co-unit of adjunction. And I'm going to try and find space to write that. So eta is the unit of adjunction, and then epsilon is co-unit. Yeah. Any questions?
None from me.
All right. Okay. Yeah, it's not going to be super helpful. So, as another motivating example, we haven't talked about semigroups. So if we have a set that is closed under some operation and has an associative operation but doesn't have an identity or inverses for everything, it's called an abelian semigroup. Oh, and the operation has to be commutative. And so then the groupification of abelian semigroups is basically just like taking out all of the things that don't have inverses or identities, or then adding things that give us like inverses and an identity. And so I think that there's two different words for that. Yeah. So generally, when we say groupification, we mean add things to the abelian semigroup. So you add in the identity and then you add in inverses. So like if we had like z greater than or equal to 0 under addition as an abelian semigroup, then like z under addition would be the groupification of it. That's an example of an adjoint pair. So like getting an abelian group from an abelian semigroup is a map. And basically the abelian semigroup and then the groupification are adjoint pairs, or are determined by adjoint pairs. there's a big table of adjoint pairs. Um, and we're going to go through this exercise about left adjoints of forgetful functors, which are how we get abelian groups from abelian semigroups, and then in the next section of this book, sheaves from presheaves, which are going to be one of our main tools for algebraic geometry. Um, and so, hmm. Trying to think of how to introduce this. Sorry. Full subcategory, the category of A modules, adjoint. So basically, if you have a ring A, okay, yeah. Let me write this one out. So left adjoints of get full functors. So let A be a ring, S a multiplicative subset. Then S inverse A modules are a full subcategory of A modules. And then the real theorem is that the functor from A modules to this full subcategory with the like the localization at S is the left adjoint to the forgetful functor from S inverse A modules to A modules. And it makes sense that like this is a natural bijection of morphisms. And actually, this is a fully faithful functor. Oh, that's actually a very big deal. So what this is saying is that like, and how this goes back to the idea of groupification, which I'm kind of trying to avoid a little bit so we don't have to talk about semigroups too in depth. But basically, like the idea of groupification is like we're adding in these things from like the group structure that like we would have or like the set that we would have, and so there's like a forgetful functor that forgets these things, and that acts kind of like localization. So like we're adding in inverses, we're adding in an identity, but by adding in inverses, we add in an identity implicitly, right? So that's the same thing as having this multiplicative subset S inverse. And so if you let S be all of A, then, you know, S inverse A is the groupification. And then these two are adjoint pairs because there's that natural bijection between them. Kind of the same way that like we can identify the size of Z to be the same cardinality as Q. So this is kind of like an important adjoint pair. And then we're going to talk about this with presheaves on a topological space in the next section. We don't really need the table right now, though. So, does that work for everybody?
Yeah, that works.
Okay. I'm going to give us a 5-minute break. Come back by like 8:11, 8:12. I'm just going to get some coffee. Um, so, yeah. Okay, welcome back, everybody. Um, Let me know when you guys are back.
Yeah, I'm here.
I'm here.
Awesome. So I'm changing the title to Adjoints and Abelian Categories. And so what we're gonna do is we're gonna split up Abelian categories into two, maybe three lectures. Today we're gonna try and get up to complexes and exact sequences and homology. And then we're going to spend a long time on homology. um, and then we're going to forget about spectral sequences until later. Okay, I'm just gonna read this kind of like opening section. Um, and I just want to check something to clarify. Um, yeah. Okay, so since learning linear algebra, you have been familiar with the notions and behaviors of kernels, co-kernels, etc. And later in your life, you saw them in the category of abelian groups, and later still in the category of A modules. I'm actually not sure that this is true. Dr. Scott, did they teach co-kernels in your linear algebra course in undergrad or grad school?
No, kernels, but not co-kernels.
Okay, so co-kernels are the notion of so if you have a linear transformation A, which is I guess it doesn't need to be forward. A from X to Y, then its Y quotient the image of A is the co-kernel. Um, Basically the idea is that if A has an inverse or if A has a right or has a left inverse, um, it's the kernel of that inverse. Um, so
Copy
it's
that.
like if yeah, it's just kind of this general notion. And then, yeah, so later in life in the category of abelian groups, it's the same idea of like an arrow reversing kernel. Like, usually, whenever in category theory we slap the word co something onto a definition, it just means reverse the arrows and, infer what needs to be inferred. Same notion for the category of A modules. And so we will soon uh, define some new categories, certain sheaves that will have familiar looking behavior reminiscent of that of modules over a ring, the notions of kernels, co-kernels, images, and more will make sense. They will behave the way we expect from our experiences with modules and can be made precise through the notion of an abelian category. Abelian categories are the right general setting in which one can do homological algebra in which the notions of kernel, co-kernel, and so on are used, and one can work with complexes and exact sequences. Um, we will see enough to motivate the definitions that we will see in general, monomorphisms and subobjects and epimorphisms and kernels and co-kernels and images. In this book, we will avoid showing that they behave the way that we expect in a general abelian category because the examples we will see are directly interpretable in terms of modules over rings, which you can kind of like get from a second course in abstract algebra, at least by JMU standards. Some places teach it in abstract one. Um, in particular, it's not worth memorizing the definition of an abelian category, basically because they're just the things that we work with. Um, Two central examples of an abelian category are the category of abelian groups and the category of A modules, which are, of course, kind of like a superset of abelian groups. The first is a special case of the second, and as we give the definitions, you should verify that A modules are abelian categories. First, we will define the notion of additive categories. We will use it only as a stepping stone to the notion of an abelian category. Two examples you can keep in mind while reading the definition: the category of free A modules, meaning A module, finite abelian groups. Nope, no, any A. So any A module which is not finite has no finite generators. So if you think of this in terms of in terms of abelian groups, um, it's all of the abelian groups which are not finite. Um, this is I don't know. I kind of want to take a quick detour to talk about torsion and the notion of free modules versus like torsions of A modules. Have either of you heard of like these words? Because we're going to be using them a little bit.
I have not.
Okay, so then a brief detour. So when we're thinking about finite abelian groups, finite abelian groups, these are the same things as Z modules. What's a Z module? A Z module is a matrix with only integer coefficients. And this means that we can basically get some weird properties out of them. And this was like the one day. So when I went to visit Princeton a few weeks ago, I sat in on this guy's abstract algebra class, and it was an undergraduate abstract algebra class, but he did a really great job of explaining this. Um, and so basically, like, when we think about operations on integer matrices, we can actually do column operations as well as row operations. Um, and what they exactly like give us when we go to row reduce something to get it into a diagonal reduction, but not like a unit reduction. What we are left with on the diagonal are what are called the torsions of the Z module. And they mean that as a Z module generated by this linear transformation, then it's a Cartesian product of Z mod the thing on the diagonal. And of course, all of the zeros and ones and minus ones that you get at the end, well, Z0 is the trivial group, and then Z1 or Z minus 1 are infinite groups. And so we say that the torsion group of a Z module is basically all of the finite abelian groups generated by things on the diagonal. A Z module is free um, if if it has no torsion, basically. So like torsion groups are kind of our notion of like finite abelian groups, but they get a special name for other reasons. So is that like a helpful clarification for people?
Yes, it is.
As much as possible.
Okay. Yeah. So when we're talking about free modules, we mean like just not finitely generated modules. Um, okay. So abelian categories. So definition. Script C is called an additive category. If and only if we satisfy the following three properties. One, for every A and B in script C, the morphisms between A and B is an abelian group. What do we mean by this? Well, we're thinking of this under the operation of function composition, right? So when we defined the symmetric group a way long time ago in abstract algebra, we said, okay, the symmetric group is like all of the permutations of a set, and the operation on these functions is function composition. So basically, for any two objects in the category, its morphisms form an abelian group under function composition. And then also is an abelian group such that composition distributes over addition. That's kind of a key part. And this is our notion of bilinearity, right? So like f of g plus h is equal to fg plus fh, and g plus h f is equal to GF plus HF, but because it's an abelian group, these things are also equal. Right? Letting F, G, and H all be in the morphism set or morphism class of the category. Does this make sense?
Yeah.
Okay. So then, and C has a zero object. So this is what is really important for us to be able to set up homology and cohomology is we want to be able to define short exact sequences and long exact sequences. The way we do that is, well, we need to have a zero object. I think I've introduced this before. I'm just going to give like a little teaser for next time, but a short exact sequence is something that looks like this, where G circ F is equal to 0. And then an exact sequence, the thing that makes it exact, is if the kernel of F is equal to the image of G is a short exact sequence. So this motivates the rest of homology, cohomology. So reason why that's important is that you have to have like an abelian category to have like well-behaved short exact, long exact sequences. And yeah, remember, zero objects are initial and final objects. So there's an arrow to everything and an arrow from everything. And then finally, C has arbitrary products. Arbitrary finite products. And this is so that we can kind of like define the limit of a category nicely, or like the fibered product nicely. In addition, morphisms in abelian categories, morphisms in abelian categories are called homomorphisms. So like groups are an abelian category. And here's the key notation. More AB is now denoted hom AB. And so this should hopefully clarify for you guys that like we've seen abelian categories a lot when we've been talking about A modules because, well, what have we used instead of more? Well, we've used hom. So we've been talking about abelian categories this whole time. Or sorry, additive categories. But they end up being abelian, right? Like abelian is a special case of additive. Additive categories, preserving the additive structure. Sorry, a functor between additive categories, preserving the additive structure of hom is called an additive functor. Usually we take this for granted. So, now Vakil has a bunch of remarks. Okay. So it is a consequence of the definition of additive category that finite products are also finite coproducts, so like direct sums. The details don't matter to us. So the direct sum symbol is used for this notation. Also, it is quick to show that additive functors send zero objects to zero objects. And then additive functors preserve both identity morphisms and zero. And they preserve products, which is nice. One motivation for the name zero object is that the zero morphism in the abelian group hom AB, and this is important to write down, definition, whoa, that F did not come out of the factor right. So the zero morphism in the abelian group hom AB um, is the composition A to 0 to B. Um, and so kind of a cleaner way to axiomize additive categories once you know that the abelian group structure is there, is to say that it has a zero object and that products of any two objects and coproducts of any two objects are contained in the category. Um, by universal property of product and coproduct, we have natural isomorphisms between coproducts and products. So, in additive categories, products are isomorphic to coproducts. This gives us a natural composition. Well, for some stretching of the word natural. Coproduct B to B. And then this is our isomorphism. This is called the codiagonal map, defined by the universal property of the coproduct. By universal property of coproduct. And then this is yeah, I mean, okay. I don't think the rest of the remark needs doing. Yeah. So any questions on this remark or on this definition about the zeromorphism?
No.
Okay. Oh, we're like making good time. Okay. So definition. Let C be a category with a zero object. So let C have 0 in ob C. Then a kernel of a morphism F, where F is a morphism from B to C, is, and I'm just going to make clear we're defining the kernel, is a map I from A to B, with F circ I equal to 0. And then that is universal. So this is sort of saying the same thing that we've always known about kernels, but it takes a little bit of work to get there. So this naturally comes through a commutative diagram. So if we have I, we have F, we have some morphism into B, we have a unique factorization here, and then we have the zeromorphism. So the morphism from A to 0 to C factors through B, and then the kernel of F, this thing, is the stuff which goes into B, but ends up zero or like being 0 in C. So I is the morphism like into B so that we get everything that we don't want through F coming out as 0 in C. So the kernel is not just an object, it is a morphism of an object to B. In practice, the term is often applied to just the object, and the intended interpretation is clear from the context. And so usually we write it just as if it's an object. Notably, like A is an inclusion of B. Right? That's the reason why we have I here. I just realized I need to plug in my laptop. But like A is an inclusion, or sorry, A is included in I. There is like this inclusion map from A into B. Is this a clear definition? I know that this is not like the usual way that we think about this, but like another way to think about it, right, is well, we define the kernel in linear algebra as, well, okay, we have a basis for the kernel of all of the vectors which zero out when being multiplied into this matrix. Well, that is a linear transformation, right? Like we don't treat it as one because we say, oh, well, we just want to consider the objects, which are vectors that zero out through this linear transformation. But really, it is a linear transformation, and it's a subspace, right? We know, like in Z modules or in the category of groups, the kernel is a normal subgroup of the domain of a homomorphism. So we've always kind of thought of it as both an object A and a morphism I. Does that make sense?
Yeah.
Okay. So a co-kernel is defined dually by reversing the arrows. So a co-kernel, which we'll usually call coker F, is the dual of the kernel of F. So is the dual of ker F, and like as a remark that helps with this construction, the limit of the diagram B to C through F to 0 goes goes like this. Lim of the category is I is the kernel. And so then what I had drawn out for the co-kernel diagram is that the kernel object, so if you have A going into B, which goes in to C by Q, and this A goes F. Then Q is the co-kernel of F, and A goes by G into Y. Oh, this isn't C, this is Q, which is the object of the co-kernel. And then U is the unique factorizing thing, and Y is 0. Hold on. I think this might be error reversed. It is, oh, yeah. So the co-kernel of F is this thing from B to Q that zeroes back to A when we reverse the arrows. I think my explanation earlier without the diagram might have been more intuitive. Does this make sense to you guys?
Yes, it does.
Okay. Like, okay, I'm just gonna phrase this in a linear algebra way, right? Like, example, like in linear algebra, if A is a linear transformation from V to V prime, um, then, ker A is the set of vectors in V such that, AV is equal to 0. And then if B from V prime to V is such that BA is equal to the identity in V, which we can always construct, right? Um, then the co-kernel of A is the kernel of B. So basically, it's the kernel of the left inverse, is our intuition. Intuition, co-ker is equal to kernel of the left inverse of a homomorphism. Does that make sense?
Yeah, that really makes sense now.
Okay.
Yeah, it
Yeah.
does.
Yeah. So this is really what we're talking about. Um yeah. Okay, so then our big definition is an abelian category. Um is an additive category satisfying three more things. Um so every map has a kernel and co-kernel. Every monomorphism is the kernel of its co-kernel. Every monomorphism is the kernel of the co-kernel. And again, think about this as like it is the kernel of the co-kernel of the kernel. Or I guess rather it's the kernel of the left inverse of a morphism. right? And then every epimorphism, so like surjection, is the co-kernel of its kernel, which we mean to be wow, that's terrible. Hold on. I'm trying to wrap my head around how to put that in terms of linear transformations. Every epimorphism, so a surjection, is the co-kernel of its kernel. So the kernel of a surjection is this prior inclusion map of stuff that gets mapped to zero through it. And then its co-kernel is the thing that I think you do actually need the commutative diagram for this. Okay, so hold on. Remember from the last seminar, or was it this? I think it was this, where we talked about epimorphisms. No, it was the previous one. Wow. Yeah, so epimorphisms are, so pi is an epimorphism from y to x, so it's a contravariant functor from x to y, um, in the category of categories, or just error reversing. Yeah. So y to x through pi is an epimorphism, is the co-kernel of its kernel. So if we have 0 going like this, and its kernel lives in here, cur pi, and then this is the co-kernel of its kernel. The kernel is the thing which goes to 0 with pi as an inclusion. The co-kernel is the error reversing, which goes to 0 as a right thing. So coker pi equals 0. No, pi coker equals 0. Sorry, I'm talking a lot. So cur pi composed with pi is equal to 0. The co-kernel of pi composed with pi equals 0. Does that make sense?
Yeah, it does.
Okay. And so then this thing is an epimorphism if pi is coker of cur of pi. And so then what this means is that the co-kernel of the kernel of pi composed with the kernel of pi equals 0. I'm going to copy this entire thing over. Okay, and now that makes sense. Okay. This does become very important for like homological algebra because we're going to prove this thing next lecture, hopefully called the snake lemma and the five lemma, um, that deal heavily with like kernels and co-kernels commuting or not. So like understanding like what of this works certain ways, yeah, it's just going to be very important. Okay. Um, it is a non-obvious and imprecisely stated fact that every property that you want to be true about kernels, co-kernels, etc. follows from these three. Warning, in part of the literature, additional hypotheses are imposed as part of the definition of Abelian category. The image of a morphism is the kernel of the co-kernel. Wow, that needs a diagram. Okay, hold on. So if f from A to B, the image of f is equal to the kernel of the co-kernel of f whenever it exists, which it does in every Abelian category. And then as a corollary of this definition, A to the image of f is an epimorphism, which like you can think of as just being the surjection, and a co-kernel of the kernel of f in every Abelian category. So f is a co-kernel of mf, nope, of ker f. Into A in every Abelian category. So does that make sense?
Yeah, it does.
Okay. We will leave the foundations of Abelian categories untouched. The key thing to remember is that if you understand kernels, co-kernels, images, and so on in the category of modules over a given ring, you can manipulate objects in pretty much any Abelian category. This is made precise by the Freyd-Mitchell embedding theorem. However, the Abelian categories we will come across will obviously be related to modules, and our intuition will clearly carry over, so we needn't invoke a theorem whose proof we haven't read. For example, we will show that sheaves of Abelian groups on a topological space F or X form an Abelian category, and the interpretation in terms of compatible germs will connect notions of kernels, co-kernels of sheaves of Abelian groups to the corresponding notion of Abelian groups. Small remark on chasing diagrams. It is useful to prove facts and solve exercises about Abelian categories by chasing elements of diagrams. Unfortunately, some commonly used Abelian categories, such as the category of complexes, which we will define very soon, do not have elements. They are not naturally sets with additional structure in any obvious way. Nonetheless, proof by element chasing can be justified by the aforementioned embedding theorem, which says that if C is an Abelian category whose objects form a set, then we have a ring A and an exact, fully faithful functor from that category into some A module, which embeds C as a full subcategory. Unfortunately, the ring A need not be commutative. Basically, the upshot of this is that to prove something about a diagram in some Abelian category, we can assume that it is a diagram of modules over some ring, and we may then diagram chase elements. Moreover, any fact about kernels, co-kernels, and so on holds in mod A, holds in any abelian category. So, okay, upshot of all of this is we will prove a lot of things using A modules, and that will be our justification for anything further, I think. If invoking a theorem whose proof you haven't read bothers you, a short alternative is Saunders MacLean's Elementary Rules for Chasing Diagrams, um, and a proof of the five lemma is a good example. In any case, do what puts your mind at ease so you can move forward. Do as little as your conscience will allow. Um, okay, so I am going to end this with one definition if there are not any other questions.
None from
I
me.
have a question.
Yeah.
I'm now that you kept talking about it, I remember a little bit from my class about code kernels, and I'm trying to, I guess, get a feeling for it. And I'm reading something, and I want to ask if you can clarify. It
Yeah, totally.
says that the kernel is a way of detecting injections, whereas the code kernel can be thought as something that detects surjections. So I'm
Yeah,
trying to understand
so
what that means.
yeah, so there's this theorem that says that a function is injective if and only if its kernel is trivial, right?
Okay.
Um, and so basically, like that's how we detect like inject. It's a group theory theorem that extends to rings and then later A modules as a property of rings. Um, and so then co-kernels tell us about surjections because, well, at least in the context of this sort of mutual inverseness with the image of a morphism with like curve co-curve f. Basically, if the image of a function is the kernel of the co-kernel, um, and it is injective, then the kernel of this thing should end up being trivial,
Okay.
right?
Okay.
Um, and so moving this around to the co-kernel, um, thinking in terms of linear transformations, right? It's just the thing that goes backwards from the left of this linear transformation. And so, like, in an ideal world, a function is injective if and only if its kernel is trivial, should hopefully mean that a function is surjective if its co-kernel is also trivial, because then it's a bijection. If we're not losing anything going either direction, if nothing gets sent to zero besides zero in either direction, then like that is kind of our notion of bijectivity.
Got it. Got it. It's becoming a little clear because yeah, yeah, thank you.
So like for like one example you could do when we hop off is pick any matrix, pick two matrices, pick one that is full rank and one that is not full rank. Well, to get the kernel of the full rank matrix, it will be trivial. And so then you can look at the image of that matrix as, okay, well, the image of that matrix from that vector space to the same vector space is going to be just the original columns of the matrix. And so then the co-kernel back to the original vector space will be that previous image. But now maybe like append a few columns. Well, the image of that matrix in this new larger vector space is not going to be like full. It'll be determined by like if our original thing was like a 3 by 3 matrix that was full rank and we appended two columns, going over to R5, the image of this matrix is uniquely determined by, or not uniquely, but is determined and uniquely factorized through three columns of this first matrix. Um, and so if we move backwards, then the things that get forgotten and sent to zero will be all of the things in like it'll be two lanes of R5, so to speak. or like 2 rows of vectors in R5 that get sent to 0 appended to the bottom of R3. And that'll be going through the kernel of the left inverse of the 3 by 5 matrix that you construct. So
Thank
that's
you.
kind of like a helpful way to like.
Yeah, that makes sense because I was reading before that the code kernel gives you insight into the constraints. Now I get it. When you just said add the
Yeah.
2 columns, I get it now. So yeah,
And
thank you.
so another thing you can do with this, so again, that's in the category of vector spaces, which is a subset or a subcategory of A modules. But with A modules, what we can do is instead of just row operations, we also have column operations. Um, and so, of course, we're restricted by the nature of like the coefficients that we're drawing from, from the ring. But with column swaps and row swaps, you might want to play with like a few Z modules. Where it's just like an uneven matrix with integer coefficients and see what the resulting thing is. I can email some notes maybe about torsion groups as well, because that's kind of like an easy construction to start working with. Or maybe we'll even open up next time. I'll prep some stuff if I have time about torsion groups and Z modules as like a motivator for kernels and co-kernels, because they're pretty important for everything we're about to do.
Thank you.
Yeah. So actually, no, I am going to end it here, and then we're going to talk about complexes, exactness, and homology and cohomology next time. Um, so yeah. Any final questions before I stop the recording?
I'm good. Thank you.
All right,
I'm good
Garrett.
as well.
Awesome. Well, thank you all so much for tuning in. I'll go ahead and stop the recording now.
Awesome. Thanks, Tim.